Okay, so yeah, we're going to finish chapter 4 today. This will also conclude the probability part of the course. And on Thursday, we are going to start chapter 8, which is statistics and some statistical. So if you introduction to statistics, we're going to talk about some descriptive statistics, some graphical statistics, how we can get histograms, box plots, and things like that. All right. So, but first, let's go ahead and finish today's lecture. Where was I? Yeah, somewhere here. Yes, the central limit theorem. And also an important announcement. The midterm exam date and time has changed based on some feedback from you. We have moved it on daytime, not the evening. So it's going to be between 4 p.m. and 6 p.m. on the following day, Friday. Okay, so we have looked at your schedule as far as we have also asked this to the department administration. As far as we can see, there are no clashes for Fridays, 4 p.m. and 6 p.m. But if you have something else, another exam that we don't know about, I mean, you may be, and as second year students, you're not expected to take any technical electives or other elective courses. So, but if there may be some, it's really difficult to find a spot that is suitable for all 200 of you guys. So there may still be some clashes. Please let us know. We may give you a makeup if that's the case, but we believe Friday between 4 p.m. and 6 p.m. is going to work better for most of you. And that's why we have updated the exam date and time to 30th of April at 4 p.m. And we are going to make an announcement about the exam details soon. So we have about 10 days until the exam. So this week you should expect another announcement from us about the exam. Yeah, we are also, the exam is going to include topics including chapter 8. So we are going to start covering chapter 8 this week. But as you have seen the table of contents of chapter 8, it's really easy. So we are going to be finishing up chapter 8 nicely before the exam. So the exam is going to include topics including chapter 8. If we finish chapter 8 and start chapter 9 before the exam, chapter 9 is not included. All right, so it will include topics all the way up until chapter 8. And some of the subsections you may have noticed we skipped in chapter 3, for example, application to finance, or the Chebyshev inequality, these things we have skipped. If we have skipped it in class, it means that you are not responsible from those subsections. All right, any questions about this? Right, let's go ahead and start talking about the central limit theorem. I made an introduction last time. Basically, I gave you the theorem. The theorem is about the sums of random variables coming from any distribution. But if we have identically distributed random variables that are from some arbitrary distribution, and if these are identically distributed and independent from each other, if we select these random variables from that distribution, but if we know certain information about the distribution, like the expected value and variance. So expected value and variance are properties of any distribution. It may be exponential, Poisson, binomial, negative binomial, geometric, gamma. All right. So these in chapter 8, we are going to see how we can estimate the expected value and variance of this. This could be the sample variance and sample expected sample average can be used to infer the populations, which is the random variables actual mu and variance values. Okay, so these are not so difficult to obtain parameters. This is what I'm saying. For any random variable, but if you have a lot of these random variables, if you collect a sample from a population, you will be able to estimate mu and variance. Now, the central limit theorem is interesting, and it's very powerful in the sense that whatever the underlying distribution of these random variables are, for example, I'm going to change the example in the book a little bit to have the variables come from the Poisson distribution. So it doesn't matter of which variable, where these random variables are coming from. When the sample size you get, when n goes to infinity, if you take a lot of these random variables and take their sum, the standardized sum, which is if the sum, let's call this sum a new variable, let's call it s, all right? It basically says that s behaves like a random, the standardized version of s, in which when you standardize this s, what do? You subtract the expected value of s from this and divide it by the standard deviation of that s that you have defined the sum. So sum, expected value of sum. If each of those variables have expected values mu, the sum is going to have an expected value of n times mu because of the linearity of expectation. These are independent. It's the sum of those variables. So this is the expected sum, and if you divide it by the standard deviation of that sum, which is if the variance, again because of the linearity of expectation, the variance of the sum is going to be n times sigma square. That's the variance. If the variance is n times sigma square, it's going to be its standard deviation is going to be the square root of that, which is sigma times square root of n. So this is how we standardize non-standard normal variables, right? So if you standardize the sum, it shows you that it's the central limit theorem tells us that it's going to be normal, standard normal. Okay, so any the x1 and xn, I mean the x1 through xn, they can be from any distribution, but the standardized sum is always normally distributed. This is a very powerful theorem. And also, if this is the case, then we can ask probabilities about this. What is the probability that this standardized sum is going to be less than some standardized number? We can directly go ahead and take a look at the CDF of standard normal, which was this capital phi, and we can use this capital phi to answer questions about the original probability of about sums of these numbers. We are going to see examples where we are asked about something, a sum of something. We are going to see, for example, sum of sizes of images. If you have one of the examples we are going to solve is imagine we have some ample disk space, a free disk space that we want to put some images in. And we want to figure out, we want to predict whether before we attempt to do that, we don't actually have the images ourselves, but we know somebody tells us that, for example, I'm going to put 300 images from my camera. And we know that the camera, each image may be coming from any distribution, it doesn't matter. But we may, if we know the average image size and the standard deviation of those image sizes, we'll be able to ask probabilities like, what is the probability that those 300 images are going to fit in my 1 gigabyte free space, for example. Okay, so if you're given the mu and standard deviation of those images, we'll be able to solve examples like this without the underlying, even if we didn't know whether the image sizes are gamma or normal, it would not matter. When we are talking about the sums of those images, the total image size of 300 images, is it going to fit in this 1 gigabyte space? We'll be able to answer these questions by referring to the standard normal distribution. So that's the one application of the central limit theorem. Other applications involve having these binomial distribution, gamma distribution. In binomial distribution, when n is large, this is like a summation of Bernoulli random variables. So it's the binomial random variable itself is a sum variable. So it means that for a large n, central limit theorem applies, and it's going to be the standardized sum for binomial is going to be normal. It was going to be normally distributed. Gamma as well. Gamma is a summation of exponential random variables. So the summation is also going to be normal for large alpha in this case. So if we take a look at now, go to the book and what these sums of random variables mean and how really it behaves when n gets larger. The book examines three things. First of all, it examines the sum. When n gets larger, if we just look at the sum itself, it's obvious that as n goes to infinity, the sum itself is going to, I mean, if these are random variables with some mu, the sum is going to approach n times mu. And as n gets infinity, this is going to converge to infinity. The sum itself is going to converge to infinity, right? So if you look at the sum itself, so the central limit theorem does not is not directly about the, oh, where's my, I'm going to get Octave Online from here. Yeah, and this sum itself, as n goes to infinity, it's going to converge to infinity, and the variance itself is also going to vary a lot. But here, if you look at the average, another thing is if you look at the average, by the way, this comet graph is like, it's every time you draw a comet, it shows the last item you put in with some circle in it, and the previous items are shown as a line graph. This is what a comet graph is. We can actually try this, on Octave Online. All right, maybe I can copy and paste from here. Let's see whether Octave Online is going to, or whether the copy and paste is going to work correctly. All right, let me load the statistics package. So yeah, I think, is there anything wrong here? Random and so, yeah, let's try this one. Oh, actually, yeah. So seconds remaining. So at 15, so the bad thing about Octave Online is that, so we're currently seeing the behavior of, oh, we're seeing the behavior of all of them. Maybe let's run it a couple of iterations until n200, for example, or 400, and then let's see how it's going to behave. Okay, I'm not going to add any more seconds. Oh, now the other one started. The first one was the sum, I guess. So the sum was converging to, it wasn't converging to anything. So it's just behaving erratically. So let's see. Oh, and this was the second one. Wow, wow, we shouldn't do it like this. Each graph is shown one after another. In order to view it as an animation, we should try these one at a time. All right, so this for loop. So for example, let's try this one. Yeah, and is this common and pause. So this for loop ends here, and it just fills in this one with some random values. All right, and this rand n is a function that samples from the standard normal. So if we write rand n, it's going to give us some standard normal variable, sometimes positive, sometimes negative. So they are actually centered around 0 with a standard deviation of 1. We could try different things, like we can, instead of using rand n here, you can use the Poisson random give some lambda, for example, Poisson random 14 or 10. So Poisson random is going to give you random values, random integers, since it's a discrete distribution, between 0 and infinity, which with the mean value lambda, which is 10. All right, so you can try it with Poisson random. And what we're going to do is, if you sum a lot of numbers in this Poisson random, the summation is going to converge to a large thing. But if you look at the average as n goes to larger, some large values, you're going to see that the Poisson random variable with lambda is equal to 10, this second thing, the division of that summation with n, whatever n is, this value is going to converge to 10, all right? Because if we are sampling from Poisson with lambda is equal to 10, this second thing here is going to approach to 10. The thing that is interesting here is this one. Instead of dividing it by Sn, and if you divide it by square root of n, you're going to see that it's going to converge. It's not going to converge to 10, and it's going to sometimes be less than 10, larger than 10. It's not going to be exactly at 0. This is not because this one was using standard normal variable, and therefore, if you just look at this value without standardizing it, it's going to be like sampled from normal distribution with mean is equal to lambda and the standard deviation equal to the standard deviation of that Poisson random variable. All right, so this is basically you may try this later on your own computers, but here this one is just saying that this one doesn't converge at all as n goes to infinity. The actual sum just blows up to infinity too, and it has infinite variance. If we divide it by the number of variables we have, it's going to converge to something which is going to converge to its mean value. Okay, this is like if you divide it by n, it's going to converge to its mean value. But if you divide it by square root of n, it has a strange behavior. It doesn't converge at all. It behaves like a random variable itself. So this is the thing that leads us to the central limit theorem, which tells us that if we name this random variable Zn, which is the sum of n random variables, and if you standardize, so Zn is the standardized version actually. If we call this sum, the random variable sum, as Sn, sum of n random variables, if we subtract from it its expected value and divide it by its standard deviation, which I showed you on the slides, these are all this right hand side here, n times mu, and divided by square root of n standard deviation, the standard deviation of the sum. These are all coming from linearity of expectation that we talked about in chapter 2 or chapter 3. And this one is standard normal. So we can, this Zn, we can use this capital phi Z to ask questions about this large sum of any variables coming from anywhere. So we can actually go ahead and talk about how this is applied on some examples. Here in this one, a disk has free space of 330 megabytes, which is it likely to be sufficient for 300 independent images? So imagine we have 330 megabytes of space and we have 300 independent images. Each image, I have a question. Let me try to answer before we go into this example. No, Sn is not always less than this. So n times mu is the expected value. Sn can sometimes be larger than that, sometimes be less than that. So sometimes Zn can be negative, sometimes it may be positive. So what it's saying is that we are going to, if we divide this, so if we don't divide it by the square root of n times standard deviation, we are going to get some negative and positive values which are large, depending on how Sn behaves, whether how large those individual xn, x1, x2 is. So the expected value is going to, for example, it's like this. Imagine you have the expected value is 10, okay? If you're going to get 300 samples from this, what you get, if the average is 10, you expect to get 3,000, right? If you sum 300 values, each of which is 10 expected value, if you sum them up, the expected total sum is 3,000. But sometimes you're going to get 2900, sometimes you're going to get 3200. So it's going to, this summation is going to be, and this numerator at the top here is sometimes going to be negative, sometimes going to be positive. Okay, so this one is always, so here, when you're asked about this probability, this one being less than z, z can here be, for example, if you look at the standardized sum, it can sometimes be negative, it can sometimes be positive. When we're asked about, we will be asking, for example, what is the probability? So this z is the standard deviation. Our probabilities may have things that ask what is the probability that it's larger than the sum, or what is the probability that it's less than the sum, depending on what type of question we ask. This is shown here as less than z because it's the CDF, the cumulative distribution function. And this z here can be negative, positive. It's just a normal distribution. So let me just get this a little bit up and get my GIMP. So it's like z is going to be, so this is the z-axis, and it may be positive, it may be negative. So it's asking, if you ask a probability about z being negative here, what you're looking for is going to give you this less than z probability. If you're asking a probability about a positive z, you will be finding this probability by referring to the standard normal CDF. So this one does not tell us anything about what we get here when we standardize any random variable. We may get negative or positive values. Okay, and this z, we can actually use the non-standardized version if you're asking probabilities. Like, yeah, think about the example that I gave. It was the expected sum was 3000, right? 300 elements, each of which with expected value 10. I expect the expected value is 3000. I may ask things like, what is the probability that the summation is less than 2700? Or what is the probability that the summation is less than 3300? Okay, both of them are probabilities that I can ask. Okay, if the expected is 3000, I may be very conservative and I ask, what is the probability that it will be less than 2700, which is in this case less than the expected value, and therefore we're going to get some negative value from here. And this 2700 is going to be standardized too as well. So the z that I'm going to get for 2700 is going to be, when we see this question, you're going to see sometimes we can get here a positive z value. If I ask the same thing, if I had a disk space of 270 megabytes, the right-hand side will be a negative value in that case. So depending on what the probability that you're asking, the z value here, the thing that you will get here may be positive or negative. So it's just standard normal. We can be fluctuating around 0. Both negative and positive values are possible. So I think it's going to be more clear after this example. So yeah, we have 330 megabytes of space. Now we have 300 independent images. If each image has a mu value, the average 1 megabyte with a standard deviation of 0.5 megabytes. So both of them are in megabytes here. If we know these things, we may ask, so what is it likely to be sufficient for 300 independent images? So what we're asked is, what is the probability that the non-standardized, so in the non-standardized version, we are asking what is the probability that the summation is less than 330, right? We're asked this probability. We have 300 images, let's call this random variable Sn. What is the probability that it is less than 330? This is the probability we are asked. The central limit theorem says that the standardized version of this is a standard normal variable, which means that you have to also standardize the thing that you're asking, 330. The expected sum 330, if you subtract from it the not the expected sum, the sum that we're asked, the free space that we're asked is 330. If you subtract from it the expected sum and divide it by the standard deviation of the expected sum, which is 0.5 times square root of n. So this is the standard deviation of the sum. So this is really interesting. It shows you that the sum itself has a larger variation than individual items, right? In the individual items, individual images have a standard deviation of 0.5. But if you look at a summation of 300 images, the summation itself doesn't have a standard deviation of 0.5. It makes sense, right? Because each of those small things have a standard deviation of 0.5. If you look at 300 of them, they have a larger standard deviation. And the standard deviation does not grow linearly as the number. The variance grows linearly, but the standard deviation is the square root of variance. Therefore, as the number n increases, the standard deviation does not increase that much. It increases sublinearly with the square root of your sample size. Okay, so this is the standard deviation of that sum of 300 images. So when you do this, when you convert this non-standard variable Sn to a standard variable, this is what you're going to have on the left-hand side. This is your standardized sum, and the probability that these two probabilities will be equal. So you will be looking, if you call this standardized variable z, the probability that z is less than this, we can compute this 30 divided by this. It's going to give you some z. So it's going to be actually 3 times 46. So we will be looking at phi 346. This is directly the CDF. We are looking for whether a random variable x is less than some z. If that z turns out to be 3.46, you'll see that it's going to be here. Yeah, it's going to be so you have a lot of space. The probability that this one is less than 330. So what we did was here 330 is standardized. So the probability that what the sum we are going to get is less than 330 is a large number. So this 330, in other words, let me again just show you the same figure. So it was like this. We had something like this, 300, and 330 falls somewhere here, right? So it's basically asking, what is the probability to the left here? This sum itself, I mean, if you look at different values of the same 300 sum, as n goes larger, sum itself goes to infinity. But if you take a lot of samples of size 300 and look at all those sums, that sum itself, the histogram of sums of 300 is going to look normal like this. Non-standard, it's going to be centered around 300, and it's going to be normally distributed. This is also saying something about the sum. So if you standardize this, which means that if you make it 0 and rescale it so that the standard deviation becomes 1, this becomes standard normal. So the probability that we're asking is this 300 larger than 330. How larger 330 is compared to this 300? And we see that based on our standard deviation we are given, standard deviation of 0.5 megabytes per image gives us that this 330 is actually 3.46 standard deviations larger than the mean, which means that if these are normally distributed, if you're this many standard deviation larger from the mean, the probability that the actual sum Sn is going to be in this somewhere in this region is great. The probability is like 0.9997. So this is basically intuitive description of what we have just done. We asked the probability. This was our random variable, the actual, not the actual, but it's the random variable, the sum of those 300 images. We don't know what they are. It's a random variable. Okay, so it may be anywhere in this region. It may even be this, but with very small probability, because if you plot this normal distribution graph, and if the standardized normal, this 330 becomes 3.46 standard deviations larger than the center. So you're most likely, when you sum those 300 images, they will most likely, with 0.999 probability, whatever those image sum is going to fall in this region. This is basically telling you that. All right. So yeah, this also tells you that the sum itself, we didn't use the non-standardized sum, we didn't call it as a normally distributed variable, but if you fix this n to 300 and you take a lot of samples of 300 images, you see that it's normally distributed with mean, it's normally distributed with expected value n times mu and a standard deviation sigma times square root of n. So this is the non-standard. Any standard variable could be non-standardized, right? So this is that non-standard. Sn is that non-standard version. So the sum of 300 images is also a normally distributed variable, the sum of 300 images, but it's non-standard. So if you try to plot it like this, it will, if you take a lot of samples of 300 images, you'll see that they are, the sum is centered around 300, like this, the histogram, and 330 is going to be 3.46 standard deviations away from this. But the standard version is used to solve these probabilities because we have the standard normal table we usually refer to. Now I think this one is an example in which we are ask a different probability, not less than. This time the 1 minus CDF is going to be used, I think. So this is an elevator problem. We are waiting for an elevator whose capacity is 2,000 pounds. So the elevator comes with 10 adult passengers. Suppose your own weight is 150 pounds. Okay, so this 10 is not that large number, but we can still, oh, okay. Now, this is a good example in which we cannot actually apply central limit theorem for this. So this was like a trick example in under section central limit theorem, because this 10 is not a large number. Okay, usually in order to apply the central limit theorem, n should be at least 30. That's the rule of thumb, but the 10 is not a very large number. If the weights are not normally distributed, we cannot use the standard normal table to solve this question. However, in this question, there's some other information that is given to us, which helps us to use the standard normal distribution. It tells that the human weight, we heard that the human weights are normally distributed. Okay, so if the individual random variables are normally distributed by themselves, even if that n is small, 10, 5, the sum is going to be normally distributed. Okay, so that's another thing. So I don't know whether it tells us here. So it doesn't talk about that here, but this is an important. Oh, okay. Yes, this is in the spatial case of normal variables. So it's just before the example. It's the book states this: even for small n, if the individual random variables are coming from normal distribution, the theorem, the central limit theorem, applies for the sum too. If the individual random variables are normally distributed themselves, even for small n, we can apply the same strategy we have used. All right. But if we didn't know that human weights are normally distributed, if they were distributed, maybe Poisson or not, or gamma distribution, for example, may be suitable for human weights. If that was the case, and then we would not be able to apply this for this question, because this 10 is not a large number. Central limit theorem applies when we have large numbers, and especially most of the time it's like 30 is the numbers that you're looking for. Okay, now let's look at this question example. Then I'm going to conclude today's lecture with binomial approximation, normal approximation to binomial. So our own weight is 150 pounds, and we heard that human weights are normally distributed with the mean of 165 pounds with a deviation of 20 pounds. Would you board this elevator or wait for the next one? Okay, so there are 10 people in the elevator already, so you're looking for whether the sum of these 10 people plus your weight, you know, your own weight, which is not a random variable. So 150 is written here. It's not a random variable. The random variable is this. So in other words, you're asking a question whether the sum is less than 1850. So you subtract this from the right hand side, okay, if you will be asking this question by putting this on the other side, by leaving the random variable on one side. Okay, if the probability that those 10 passengers have more than 1850 pounds, if that's you're asking that probability, if it's less than that, you will be you want to board the elevator, but you're looking at probabilities. Okay, so what we do is we first again standardize the left hand side. This becomes our standard random variable. This becomes our z, okay, the standardized random variable. And the probability that we're asking is this one. If you standardize it, you again subtract from it n times mu divided by 20 times the square root of n. So this is our standardized probability we're asking. It becomes 3.16, okay? So which means that it is, so 3.16, the probability, the right-hand side is 3.16, which means that 2000, the 2000 is going to be, or 1850 is going to be larger than this. Again, the sum that we're going to get here, the actual random variable, the sum of those 10 people are going to be on the left-hand side. I mean, they're going to be this much. So we are looking at the probability that they are larger than that. So in other words, let me again draw this on GIMP. So it's something like this. So we have when we do the summation of those 10 passengers with 165 each is something like this, okay, and this 1850 is again to the right hand side of this, all right, and we see that after we do the standardization, we see that the difference from this mean is 3.16 standard deviations larger, meaning that the sum, the random variable we have here, the summation of those 10 people is most likely going to stay in this region. The probability that we are looking for, the probability that this z is less than 3.16, the probability that the summation is less than this is going to be a large number again, 0.992, something like that. Let's see. Yeah, 0.9992, another 9. So it's a very small probability. So we were asking, what is the probability that they will exceed, the probability that the summation is going to exceed 1850 is going to be 1 minus this 0.9992 probability, which is, there's a very small probability that these 10 people are going to be weighing more than 1850 kilograms. Okay, so this is how we apply the central limit theorem. This standardization of random variables and standardization of the values that we're asking the question, you may get used to solving problems like this by solving some exercises at the end of this chapter. And this week's quiz is also going to be about chapter 4 and about central limit theorem probably, or normal distribution. So you will also have a chance to experience to practice central limit theorem also with the quiz. Yeah, negative binomial, gamma variable, they're all, they can be approximated by normal distribution. And the final thing that I'm going to discuss today is the normal approximation to binomial distribution. And that's something strange because binomial distribution is a discrete distribution. It's the number of successes in n trials where each trial has a success probability of p. That's what a binomial distribution, binomial variable is. So it's a strange approximation because binomial distribution is discrete and we have normal distribution is continuous. When we ask a problem about binomial saying that what is the probability we are going to get 5 successes in 10 tries where the success probability is 0.3, okay? In this case, if you just use normal approximation and try to figure out what is the probability of exactly obtaining 5 successes, normal distribution is going to give you 0 because point probabilities are 0 in continuous case. So it's again, let me go to GIMP and see what's going on. So what's going on here is that if this is a binomial random variable with some n and p, what we are going to observe, and when n gets larger, we are going to observe an histogram that looks like this. It's going to still be PMF, probability mass function. Whatever n times p is, you're going to get values that are around n times p, and maybe they will be getting smaller and smaller like this, and it's going to be symmetric. So actually there's a MATLAB code for that in the book. So look at this. You may there's a MATLAB demo to have the binomial distribution gradually takes the shape of a normal distribution when n gets to infinity. So as we increase the size of this, we may get the binomial probabilities also approaching something like this. So we are going to see a symmetric PMF around n times p. So this is what it's saying. Now, the binomial, the normal approximation to this binomial distribution, on the other hand, when we do have a normal distribution, which we get mu is equal to n times p, and the standard deviation is equal to, what was the variance of binomial distribution? The variance was p times q, right? Or n times p. Yeah, this was the variance, if I remember correctly. N times p times q was the variance. P times q is the variance of a Bernoulli variable. The variance of the binomial variable with n tries, that's the variance. It means that the standard deviation is going to be the square root of this thing, p times q, which is q is 1 minus p. Okay, so what if you draw a normal distribution with these parameters, this is n times p, you're going to get something like this. So this is your normal distribution centered at n times p with a standard deviation of n times p times 1 minus p with all those parameters given. Okay, so this is how we are going to get normal distribution. So this red one is normal distribution. So when we are asked the probability, for example, what is the probability that for a binomial variable, what is the probability that binomial variable that is equal to, for example, n times p plus 3? If you're asked a probability like this, n times p plus 3, 1, 2, 3. So we are asked this probability. By applying the probability mass function, we should get this probability here. But if that exact point, n times p plus 1, is this point here, n times p plus 1. If we look at the probability, so we cannot, the PMF function, by the way, the probability density function doesn't give us probabilities, right? The height of this curve is not, in the continuous case, is not the probability. And therefore, also point probabilities for continuous cases, the probability is going to, the normal variable on the, if you ask the same thing for your normal variable, what is this probability, it's going to tell you that it's 0, because the area under the curve at this exact line is going to be 0. So what we do is actually something very intuitive. We enlarge the point probability that we ask for normal distribution 0.5 units on both sides. So it's like we're trying to approximate the area of this rectangle by extending this normal distribution curve 0.5 units to the left and 0.5 units to the right around the center probability that we're asking. So we compute this probability and use it to approximate these point probability mass function for binomial. So this is how the approximation is done. This is called the continuity correction, if I'm not mistaken. So let's go to the slides. Yeah, so that's called continuity connection. So this is our binomial variable with n parameters n and p. If n is large, this is closely the histogram of it and its probability mass function. And normal distribution can be used, and by applying the central limit theorem, you're going to have a normal, the sums of Bernoulli variables will be normal. So when we're asked a probability about the Bernoulli binomial variable x, actually this x is that normal case. If we have a binomial variable b and we want to find the probability of b being equal to this b, and this will be 0 in the continuous case. Therefore, what we do is we find the probability of this b minus 0.5 plus 0.5 to solve it in the continuous case. So we expand the interval 0.5 units in each direction. And this b is always going to be an integer when we're asked probabilities. When this is a discrete random variable, it means that we have integers, right? So this is always going to be an integer, and when we are asked the probability of, for example, what's the probability to become 9, we'll have to do the integral from 8.5 to 9.5 in the normal case. When we're asked probabilities that have inequalities, for example, the CDF of, if you're trying to find the CDF of binomial, let me write here. So CDF of binomial, for example, 9, if you want to compute this, what you're going to do is the CDF, the probability of x less than or equal to 9, right? This is what the CDF shows us. So you're going to extend this 0.5 units to the right. So it's going to be in the normal case when we're when we want to use the normal distribution or the standard normal. Actually, this 5 is standard normal, this 9 is not standardized yet. So when we look at the normal distribution with the same thing, the CDF normal, let me write it CDF normal, I will have to ask the same probability for 9.5, all right? Because the probability mass function, this binomial variable, when we ask the CDF of 9, it includes the probability mass function of 9, right? Which is between 8.5 and 9.5 when it's continuity corrected. So when we're asked a CDF like this, we need to extend it 0.5 units to the right and take the integral. So CDF normal 9.5 will take the integral from minus infinity to 9.5. All right, so we have to do continuity correction in one direction only if the left-hand side of the interval is completely included. So what I'm trying to say is that if you look at the CDF of 9 here, if this was 9, it's going to be extended 0.5 units to the right, and then we just integrate all the way to minus infinity, from minus infinity to 9.5 to approximate the CDF of binomial. And let's quickly take a look at this example 4.15, which is very simple. Let's quickly go over that in 1 minute, and this is going to complete our discussion of chapter 4.15, right? It was, yeah, 4.15. So a new computer virus attacks a folder consisting of 200 files. Again, we have some files. Each file gets damaged with probability 0.2, independently of other files. What is the probability that fewer than 50 files get damaged? Okay, so you can see this doesn't look like an application of central limit theorem, but this here again, since binomial, we have 200 tries and the success probability of 0.2. So we expect the expected number of files that are going to be damaged is 40, right? If you multiply these two things, you're going to get 40. So we expect 40 files to be damaged. And that 40 is, is the expected value of a binomial random variable, the number of files that are going to get damaged. What is the probability that fewer than 50 files get damaged? So we are asked the CDF of 50 in this case. The normal, if we apply the normal approximation, since this 200 is a large number, larger than 30, the expected number becomes 40 and the standard deviations become 5.6. By applying the central limit theorem, the probability that this is fewer than, it's not CDF of 50, it's actually CDF of 49, right? Because it says less than 50. In the binomial case, if it said less than or equal to 50 files get damaged, then it will be CDF of 50. But it's asking less than 50 files, so 49 or less in the binomial case. So CDF of 49. So therefore, the CDF of 49, we extend the CDF, it includes 49, we extend it 0.5 units to the right, it becomes our normal random variable. We first standardize it by subtracting the mean and dividing by its standard deviation. It tells us that it's 1.69, 68 units to the right of the mean, 1.68 standard deviations to the right of 0, and the probability that it's going to be less than that is 0.95. Okay, so this is how we applied, and the description that why we extended 0.5 units to the right of this 49 is explained here. Okay, so because the interval is 0 and 49 in the binomial case, and this is the CDF of 49 as I explained here. If this here is 49 and we are looking for CDF of 49, the PMF of 49, the probability that 49 should be included in the CDF, therefore we extended 0.5 units to the right. All right, and another important thing is when you use normal distribution to approximate continuous distributions like gamma, we don't do continuity correction at all. We don't do this extension 0.5 minus 0.5 if we are using normal distribution to approximate another continuous distribution like gamma. All right, so this concludes our discussion of chapter 4. And we are going to start chapter 8, statistics, descriptive statistics, and some graphical statistics. We are going to talk about these on Thursday. I'll be happy to answer if you have any questions. Let me stop recording now.